have a break. Спасибо.
Joshua, are you ready to start?
Yeah. We can start.
Okay, great. Andy, are you ready?
I'm ready.
Yeah, great. Okay, so we have big pleasure to have second talk by Andy Neitzke from Yale about spectral network and connected stuff. So, Andy, the floor is yours.
All right, great. So like last time, please interrupt me when I say something that doesn't make any sense to you or that you want to know more about. So that was very helpful last time for me and hopefully also for you. So let me just very briefly remind you what we talked about last time. So I talked about a construction where you start with a compact Riemann surface C and the data of a tuple of differentials phi1, phi2 up to phi n, where phi I was a meromorphic I differential on C. So in other words, what is that? That just means locally it would be something which would be written some function of z dz to the I. And I usually took phi1 is 0, and in fact today throughout the day I'll take phi1 is 0. So I'll just take phi2 up to phi n. And yeah, I think that was it as far as the data. Oh well, also we had the data of a phase, theta in R mod 2 pi z. Okay, so that was the data that I had, and from that data we produced various things. We produced the spectral curve, a covering of C, branched n-to-1 covering, sitting inside of the cotangent bundle. We produced this kind of auxiliary curve, which I called the root curve, sigma twiddle, covering C, which was an n choose 2 to 1 covering. So essentially a sheet of the root curve was just a choice of 2 sheets of the spectral curve. Maybe I'll write the equation of the spectral curve just to remind you. So it was just given by the equation whose coefficients are the phi's. So it was a polynomial equation of degree n whose coefficients are these phi's. So y to the n plus phi 2 y to the n minus 2 plus phi 3 y to the n minus 3 down to phi n is 0. That's the equation defining this spectral curve. And we had this other auxiliary gadget that we called the root curve. And then the key thing that I spent most of my time trying to construct was this thing that I called the spectral network. W of theta, which was a collection of the sort of most precise way of describing it, I think, is it's a collection of half leaves of a foliation, a canonical foliation, f theta on sigma twiddle, which we defined last time. But generally, I don't think of it as living on sigma twiddle. I think of its projection down to the base. So let me show you a few pictures of what that projection could look like, just as kind of examples. Remind you from last time, the kind of thing that it was. So, okay, hopefully this works. So here are some pictures. Yeah, good. Let's make it a little smaller. Oh, sorry about this. Get it in the right place. There it is. Okay. Can you see these pictures okay?
Yeah.
Okay, so these are 4 kind of basic examples. And these are all relatively simple on the spectrum of possible examples that there can be. So in the first two examples, I just took n equals 2. So in that case, we just have a quadratic differential, and I took, so the very simplest thing you could take, well, very simplest thing would be to take like a constant or something, but the next simplest thing would be to take z dz squared, and so that's what I showed here. And so it has this characteristic behavior that every zero of the quadratic differential, every simple zero, and I generally assume simple zeros, every simple zero emits these 3 trajectories. So here you see the 3 trajectories coming out just in straight lines. Here's a slightly more interesting one, again with n equals 2, but now I took a cubic polynomial, and so each one of the zeros emits 3 trajectories, and they go out, and at very large distance they kind of accumulate in 5 distinct directions. And in general, if I took a polynomial of degree d, they would accumulate in d plus 2 distinct directions around the circle. These examples with n equals 2, this is a very well-known thing called the trajectories of a quadratic differential. It's not something new. But then when we went to higher n, sometimes I call n the rank, so higher rank, then as I told you, the construction becomes a little more interesting. So here's n equals 3 with a quadratic differential 3 dz squared and a cubic differential 1 minus z squared dz cubed. So I'm just writing the quadratic and then the cubic. And now it has this new phenomenon where the trajectories, okay, so I remind you, the trajectories really lived on this, secretly lived on this covering space. And the way that I represent that on the, in drawing these pictures on the base, is that I label them with a pair of sheets of the covering. So for example, this one might be labeled 1, 2. Let's make that a little smaller. This one might be labeled 1, 2, the first and second sheet. This one might be labeled 2, 3. And then when the 1, 2 and the 2, 3 intersect, there was this phenomenon where they give birth to a new 1, 3. And so, so you get pictures where you have some trajectories that are born from the branch points. These x's are the branch points of the spectral cover. And then there are additional trajectories that are born somewhere else. And then this last one is an example with n equals 4. So here I took a quadratic, cubic, and quartic differential, but still relatively simple ones just in the plane, and drew a picture of what you get. So that's the kind of thing that we're talking about. Very simple examples of the kind of thing that we're talking about. And what I did not do last time, unfortunately, is give you any indication of why this would be an interesting thing. So I want to try to remedy that today. Let me paste into the chat box here a link to my notes. So I have this set of notes that I'm kind of continually updating. But here's the current version, which is, I think, at least somewhat more precise than what I'm actually saying in the talk. And particularly, it's more precise than what I said last time. So I remedied a few imprecisions from last time in the first part of the notes. Okay, so now my goal today is to explain 2 uses of this spectral network. So the spectral network I call W of theta. 2 uses that are somehow connected to each other. One is in the analysis of ODEs. So some geometric aspect of the analysis of ODEs. And the second one is the theory of cluster varieties. So cluster coordinates. But they're going to be cluster coordinates on moduli spaces of local systems. So a la fucking Goncharov. And so, of course, these 2 things are somehow connected, because an ODE, when you look at the solutions of an ODE, that gives you an example of a local system. So okay, these will be 2 connected things, and then the idea is that next time I'll do the other 2 uses, or 2 more uses, in Donaldson-Thomas invariants and hyperkähler geometry. But those will to some extent build on what I do today. Okay, so that's the plan. All right, any questions before I dive in?
No, it seems like
Okay.
everybody is happy.
everyone's happy, as happy as they want to be. Okay. Great. So let's start. So I want to start with the ordinary differential equation story. Actually, sorry, before that, I want to say one more thing about the generalities of the spectral networks, which we'll need in the ODE story, which is that, so I drew the picture. I drew the picture of what the spectral network looks like in some kind of generic sense. What it looks like if I choose all parameters sufficiently generic. There's one special thing that can happen that's sometimes important, which is for a special choice of theta, what can happen is that two of the trajectories in the spectral network actually run into each other head to head. So trajectories can collide head on. So the picture would be that I have one coming this way with an IJ label, another one coming that way with the JI label. So let me show you two pictures of how that kind of thing can happen. So first is the kind of classic one. So here what I'm going to do is I'm going to hold the quadratic differential fixed. I'm going to do the case n equals 2, holding a quadratic differential fixed, and just let the phase vary. So here with n equals 2, I have a quadratic differential that has these two zeros here and here. And here I'm showing, in light gray, I'm showing the kind of generic leaves of this foliation. And then in black, I'm showing the leaves that are actually part of the spectral network, the critical trajectories of the quadratic differential. And so what you see is that, okay, for generic phase, I just have three trajectories that come out of each branch point and travel somewhere. But then as I vary the phase, there's one special phase where something different happens, which is that I have a trajectory that runs straight from one branch point to another. And that's called, so in the theory of these quadratic differentials, that's called a saddle connection. And it'll show up in our story as a kind of discontinuity, because, so you see here that the topology of the spectral network abruptly changes at the moment when you cross the saddle connection. So for example, before crossing this critical phase, we have a trajectory that goes this way. After crossing the saddle connection, the same trajectory goes in a very different direction. So in the parameter space of phases and differentials, there are these loci where something discontinuous suddenly happens. And that'll be associated as we go on to the cluster transformations in the moduli of local systems. So that's an example with n equals 2, and it's associated with this kind of classic object, which is a saddle connection. Let me also show you one example of the higher phenomenon. So when n is bigger than 2, for example, when n equals 3, we can meet a new kind of geometric objects on the surface, which, okay, part of the philosophy of this story is that we should think of them as being somehow just as important as the saddle connections. So here's an example. So here I have, so this is with n equals 3. So now I've got some location where there is where there's 3 branch points in a little neighborhood. Each one is emitting 3 trajectories as usual, and then when they collide, they're giving birth to further trajectories. And here again, as we vary the phase, there can be a kind of critical change in the topology of the picture. And here at the critical moment, what appears is not a saddle connection, but this kind of trivalent tree. In this case, it just has one internal vertex. If I would label the sheets, it's like 1, 2, 2, 3, and 3, 1 coming together. So that kind of trees or even higher topologies will appear in this story, and they'll be associated to cluster transformations on higher rank moduli spaces of local systems. Okay.
Sorry, and this is always a plane tree.
Always a plane tree.
Yeah, and how you define it in a general application?
You mean what's the most general kind of object that I would allow?
Yeah.
Yeah, so I would allow any kind of thing that's built from, the projections of leaves of this foliation obeying a balancing condition at the vertices. Let me draw. I'm not sure if this will be a satisfactory answer, but let me draw a couple other examples of things that I would allow, which I think will be faster than trying to set up all the definitions. So like, we would allow something like this. Let's draw it. Something like this, where whenever I have an ij thing, it can end either on an ij branch point, we'll just assume that branch point is labeled correctly, or it can end on an internal trivalent vertex. And when it ends on a trivalent vertex, there's a balancing condition that says that the 3 things that come into it have to be ij, jk, and ki, like that. But loops are allowed, so the topology doesn't have to be the topology of a tree. And so the possible topologies, there are many more possible topologies here than there are in the n equals 2 case. And that's part of what makes the thing, I don't know, either depending on your attitude, either interesting or unpleasant, is that there's this kind of wild proliferation of possible topologies you have to deal with.
Mm-hmm.
In the n equals 2 case, there were really only 2 possibilities. There's the saddle connection, and the other thing that can happen is there can be a ring. I didn't draw a picture of the ring, but we could have drawn a picture of a ring where, the topology of the picture looks like this. So there you have a domain that's kind of foliated by these closed trajectories. So that can also occur at special phases. But for n equals 2, those are the only 2 things that can happen: the saddle connection and the ring domain. And they're both kind of classically studied things. Whereas for n bigger than 2, there's this enormous proliferation of possible bad topologies. Okay. So anyway, for most of my purpose today, I just want to avoid these topologies. So I want a name for when it doesn't happen. So we'll say theta is a BPS phase. If this phenomenon occurs. This phenomenon of having an ij trajectory that meets a ji. And one thing you can prove is that the BPS phases there's most countably many. So most of the phases are not BPS phases. Okay. Okay, now I think I said what I need to say. So now let me start on the ODEs. or opers. So, okay, so I take my data as before. So a compact Riemann surface, an integer n greater than or equal to 1, and this tuple phi is, so now I'm not even going to write phi1, phi2 up to phi n, as before, differentials. Now I'm going to give myself a tiny bit more data, but which you should think of as kind of less important. A spin structure on C. Actually, only when n is even, I need it. And a complex projective structure on C. So what does that mean? That means just an atlas of charts that differ only by Mobius transformations. And for any Riemann surface, you can always find one of these. And so I'll just choose any one. Like, for example, if my surface is CP1, I'll just take the usual coordinate charts on CP1. Okay, so now, given this data.
Repeat, please, what does it mean, CP1 structure?
Yeah, CP1 structure. So, I mean, I think there's many equivalent definitions, but one definition is an atlas of coordinate charts. So just local coordinate charts on C. Such that the transition maps. So, the coordinate chart identifies a patch of C with a little patch in the complex plane, right? And I want to say that the transition maps, rather than being arbitrary, are all Mobius transformations, just restrictions of Mobius transformations. So I'm going to write coordinate formulas, and those formulas will not be fully coordinate invariant. They'll only be invariant under Mobius transformations. And so for that reason, you need this CP1 structure. Okay, but relatively speaking, it's kind of, this is kind of subleading. This thing is important at subleading order in this story. Okay, so that's my data. And now given this data, there's a canonical way of making a differential equation. That's what I want to say. There's a canonical, and what do I mean by differential equation? I mean an order n differential operator. So sometimes called an oper, SLN oper, if you like. SLN oper. What does it act on? Well, it acts on, say, meromorphic sections of the canonical bundle to the power 1/2 of 1 minus n, maps them to the canonical bundle to the power 1/2 of 1 plus n. So roughly speaking, it acts on functions, but with some, complicated transformation law from patch to patch. And spin structure was needed just so I can define what's k to the 1/2. But I want to write this differential operator concretely for you. So I'll say that just an example. So suppose n equals 2. Then to write it concretely, let's choose a local coordinate on C in the atlas, in the atlas given by the complex projective structure, the one I mentioned above. And then let's trivialize. So now I'm going to trivialize my bundle, kc to the 1/2 times k for any k by square root of dz to the k. I make one choice of square root of dz, and then I just use that to trivialize all these bundles. And also write my quadratic differential as phi2 is p2 of z dz squared. So then relative to these trivializations, so I meant to give this differential operator a name. I'll call this differential operator d sub phi. then relative to these trivializations, I can write d sub phi acting on a function psi. It's just the operator d by dz squared plus p2 of z on psi. So it's literally just the most obvious second order operator, d by dz squared plus multiplication by some function. That's what it is in local patches. So that's like a kind of, this is a kind of meromorphic version of a Schrodinger operator. So, you know, in like your first year quantum mechanics class, you would write an equation, d psi equals e psi, or d psi equals 0 if you absorb e into P2, except instead of having z on a Riemann surface, you would just have a parameter x on the line, and P2 would be just some function on the line. So this is, so you can think of this as just kind of a global version of that, where we live on a Riemann surface instead of on the line. So that's the kind of operator we're talking about for n equals 2. Let me also write it for n equals 3. And let's trivialize as above. And then this operator would just be d by dz cubed plus p2 of z d by dz, plus maybe the one surprising thing is that you have to write a little extra thing here. You have to write d by dz p2 of z.
In the previous example, can you be more precise about what is psi?
Yeah, so yes, hold on, let me just finish writing this and then yes. So yeah, maybe I can write it, let's write it in a slightly more longhand way. Let's write phi 2 is this, and let's write psi to be some function f of z times dz to the, let's see, I guess n is 2, so dz to the minus a half. And then the equation would be d phi of psi. The way that you get it is to apply this operator to the function f of z, and then multiply the whole thing by dz to the 3/2. Does that answer your question?
Yeah.
Okay, and a similar thing for this n equals 3 example.
And sorry, can I also ask one thing?
Yeah.
Is that right that I can think about these operas as the space of these differential equations with some change of coordinates rules, or?
Well, here I've completely written it, right? I don't have to give you the change of coordinates rule. But yes, it's correct. I mean, so right, there's some other abstract definition of what is an oper for the group SL2 or SL3. And I'm saying that every oper is realized in this way.
Mm-hmm.
So this is literally equivalent to the usual, well, to the other definition where you talk about a bundle with a flag in it and so on. But for my purpose, I prefer to describe it this way.
I see. Thank you.
Andy, I also have a question.
Yeah.
What can you say more about this choice of power of the canonical bundle that you choose? Like why specific choice of the power?
Yes, I mean, I guess the fastest way to say it is that this equation will not be covariant if you write some other power here. So like as a pragmatic practical thing, if I say that there's an operator that's given by this formula in every coordinate patch, then that implies that the equation is sort of properly covariant under changes of coordinate. And if you try to do that, if you write literally this operator, and you try to make it covariant, you'll discover it's covariant only if you put this dz to the 3/2 here. And similarly, if you have dz to the minus 1/2 here. That's a technical answer. I'm not sure if that answer will be completely satisfying. There's the more abstract answer, I mean, you can see that they should differ by n because it's an nth order differential operator. So the only chance it has to be covariant is that. Now, I think requiring. Sorry, I can't instantly give you a good answer to that.
Okay, yeah, I can come back later.
Yeah. Sorry, yeah. We can talk about it after me. Okay, but anyway, this is the statement. So we're interested in studying these kind of differential equations, and the way we're going to do it is it's one of these tricks where you introduce an extra parameter. So let's allow ourselves to rescale by a parameter which I'll call Hbar, a C-star valued parameter. So I'll define Hbar inverse phi to be the tuple where I just rescale each one by the corresponding power. So phi 2 I rescale by Hbar to the -2, phi 3 I rescale by Hbar to the -3, and so on. It's like just rescaling the whole tangent bundle by Hbar. And then I'll introduce this kind of rescaled differential operator, d Hbar phi will be just the original one where I substitute these differentials depending on Hbar. So for example, the equation that I wrote in the n equals 2 case would now become d phi Hbar of psi. Let me go back to my slightly more condensed notation. Is just d by dz squared plus now Hbar to the -2 p2 of z psi. Okay, so we just rescaled the potential part by this power of Hbar. Okay, okay, so we want to study this differential equation. What does it mean to study the differential equation? Well, what I mean is the following thing. Let's look at the solutions of the equation. So the space of solutions, sorry, I should say the equation that I'm going to be interested in is d Hbar of psi equals 0. We're going to be interested in that equation. And so the space of solutions of that equation, in other words, the kernel of d Hbar phi acting on holomorphic sections, well, that forms, if I look at a little patch of my surface, I've got an nth order scalar differential operator. It has an n-dimensional space of solutions. So this kernel forms a rank n local system. Which I'll call L Hbar phi over, not over the whole curve, but over the curve minus the poles. So C minus the poles of the phi, since the equation is singular there. So okay, so we've got, on our surface, we've got some rank n local system that comes just by looking at the solutions of this differential equation. And this local system, in the examples that are kind of easiest to access, we want to use a little bit of extra structure on this local system. So it's not just a local system, but it's what you call a decorated local system, which comes from the following. It's that if you look at any ray going into one of the singularities, one of the poles of phi, we get a filtration by the rates of growth of the sections, rates of growth of the sections. In other words, the solutions of this equation. So you look at the solutions of this equation. You look at a singularity of the equation. Then you look at the solutions along some ray, say this ray, and you ask, what you find is that some of them are exponentially growing, some of them are exponentially decaying with different rates. And so you get a filtration on this local system by the rates of growth. And this filtration typically depends on the ray, but in kind of a piecewise constant fashion. So I'm not going to develop this in detail. I'll just tell you the examples that I want to use. But this is kind of the general story. So if I look at, different rays, if I look at two rays that are pretty close together, typically I get the same filtration, but then there'll be some critical places where the filtration changes. And so what I'll get, if I think of making a little circle here, which is all the possible asymptotic directions of going into that singularity, what I'll get is a filtration of the space of sections on each. So there'll be some kind of marked points where the filtration changes. And so what I really get is some finite collection of filtrations, one for each arc on this circle. So let me just talk about kind of two key examples of this that I'll come back to as we go on. So suppose I take the very simplest case. I take n equals 2. I take my surface to be CP1, and I take my differential to be, again, my favorite one, z cubed minus 1 dz squared. So then, so it has a singularity infinity. So then I'm getting a local system just on the plane, right? It just has a two-dimensional space of sections, global solutions of the equation. So we have a space of global sections, global solutions of this kind of cubic Schrodinger equation. So write the cubic Schrodinger equation that we wrote before. Right, so here the equation is literally d by dz squared plus z cubed minus 1 acting on a function psi of z is 0. That's the equation that we're studying. It's a two-dimensional space of solutions. Let's call that space B. So it's just a two-dimensional complex vector space. And so that at first sounds like no structure at all. Like, what am I going to study? It's just a two-dimensional vector space. But then it has a little bit of extra structure coming from the growth rates at infinity. So let me paste in for you a picture. So in this case, the picture looks like this. So, okay, so I have on here again a picture of the spectral network, but you can ignore the spectral network for a second and just look at near infinity. So near infinity, I have these 5 blue marks. And those are the boundaries of 5 asymptotic domains. And the idea is if you go to infinity along a ray in one of these domains, for example, if you go to infinity along, say, this ray, or it could be this ray or this ray, it doesn't matter. Along any of these rays, what you find is that in your two-dimensional space of solutions, there's one solution up to scalar multiple that exponentially decays. One solution of this equation that exponentially decays. All the other solutions exponentially grow as you go toward infinity. And so going to infinity in this direction I've marked 4, gives me a distinguished line inside of the space of global sections, namely the line of solutions that are exponentially decaying. So inside of V, in other words, we have these 5 lines, L1 up to L5. So we got a two-dimensional vector space with 5 lines. So psi is in Li if and only if psi decays. as z goes to infinity in sector I. So I've marked these 5 sectors, 1, 2, 3, 4, 5. And for example, you could go to the dot, these dots in the middle of sector are somehow the most canonical points, but the statement is true no matter where you go inside the sector. Okay, so that's the picture of the kind of structure of the space of flat sections of this differential equation. And so so the kind of abstract data that we get from this differential equation, the isomorphism class of this differential equation, thought of as a decorated local system, is just a point. So it's the data of 5 lines in a 2-dimensional vector space. In other words, it's a point of the configuration space of 5 points of CP1, con 5 of CP1. So that's the data that you have here. You start from this differential equation and you produce a point of this configuration space. Okay, no, by the way, let me emphasize this CP1 has nothing to do with this CP1. This CP1 is the projectivization of V.
And I'm sorry, can you explain once again where did we get 5 lines from? Why 5 exactly?
I mean the numerology of it is that if you took if degree of phi 2 was d, we'd have d plus 2 asymptotic directions. That's not a complete answer to your question. That's just a first preliminary remark. So you want to know why is it that the asymptotics are kind of characterized by 5? Actually, can we return to that at the end, because we're going to do this WKB construction of the solutions, which might make it a little clearer.
Sure, thank you.
Okay, other questions?
Why is this points belong to CP1 rather than RP1?
Oh, because the equation is a complex equation, right? So this equation, that equation, it doesn't have I mean, unless I look at it only on the real line, it doesn't have any natural real structure to it. So the space of solutions is a complex 2-dimensional vector space. If you look at it on the real line, you could get some real structure, but then there's no reason why the solutions which are exponentially decaying in these complex directions should respect that real structure. So you just have a complex 2-dimensional space of solutions. There's some variant of this having to do with harmonic maps where you get configuration of RP1, but in this version, it's just CP1.
So, and what is isomorphism class? Isomorphism of the decorated local system, what it is?
So in this case, I mean, by definition, a decorated local system is just this data of a local system plus these asymptotic filtrations by order of growth when you go into any singularity. That's literally what I mean by a decorated local system.
Okay, so your statement is sort of tautology in this situation, right?
It's basically a tautology, yeah. I just want to set up the kind of general notion that, in any situation where you have a local system with these kind of singularities, there's a notion of decorated local system. There's a good notion of the moduli space of those decorated local systems, and that moduli space is something nice and concrete, like here, con 5 of CP1.
Mm-hmm. Okay, thanks.
And in general, it'll be some cluster.
Sorry, I have also another question. So
yes.
What are the conditions about the lines? Are they all different, or
it is a true fact. Okay, very good. So it is. So we get a point of con 5 of CP1, but indeed we don't get every point of con 5 of CP1 in this way. Well, in fact, using Hbar's, we miss a lot of points of con 5 of CP1. So in general, if I had written down, instead of z cubed minus 1, some more general cubic polynomial here, I think then the statement is that we would sweep out not all of con 5 of CP1, but the part of con 5 of CP1 where two consecutive lines are never equal. So like line 1 is never equal to line 2. So you don't delete the whole diagonal. It can happen that line 1 is equal to line 3, although it won't happen for this particular phi 2. But it never happens that two consecutive ones are equal.
I see. Thank you.
But actually don't know the answer to the analogous question in full generality, exactly what subset of the configuration space you get. But in this case, I think it's what I just said. Okay. Okay, so let me just very briefly remark, since I'm trying to say a little bit about the higher rank, versions of the thing, which is really what's new. If we took more generally, C is CP1, and now we took not just a quadratic differential, but some tuple of differentials. So then we get some more complicated pattern of filtrations around infinity. Let me specialize to the case where phi is a perturbation. Oh, whoops. Phi is a perturbation of 0, 0, only the last one non-zero, z to the k, dz to the n, perturbation of sufficiently low degree. So for example, I could perturb all of them by constants. Then I believe that what we should get is the relevant moduli space of decorated local systems is an open subset inside of a Grassmannian grn k plus n mod c star to the k plus n. And the above case was the case of n equals 2, and k was the degree of the polynomial. So then I'm just saying that the Grassmannian, gr2 d plus 2, mod out by rescaling all the lines, that's the same as conf d plus 2 of CP1. And this conjecture, I've checked this in a few simple cases, like for n equals 3. So the expectation is that you realize, not only configurations of points in CP1, but also Grassmannians in this kind of way. Okay. Okay, so what does this have to do with spectral networks? So now the goal is, what do we want to do? We want to be able to actually compute the map that starts with these differentials, this kind of holomorphic data, and produces the corresponding local system. So that we might call the Riemann-Hilbert map. We want to compute it in a kind of practical way. So for example, an example of a concrete thing we might want to be able to do is in the above example, we've got, L phi H bar in the configuration space of 5 points of CP1. We could ask, what is that configuration? One way to ask it would be to ask for some cross ratios. So suppose we ask for the cross ratio of the points L1, L2, L3, L5, and L5, L1, L3, L4. Those two cross ratios would give you coordinates on conf 5 of CP1. So we could ask, what are those two cross ratios? That's what we want to calculate as a function of this parameter H bar. Okay. So now I'm ready to say, what's the method? So So how do you study, how do you produce, solutions? How do you understand this local system? You need some kind of concrete way of studying the solutions of the differential equation. So we want to produce somehow solutions of this equation. And the idea is to expand the equation, is to use this parameter Hbar and to expand in a series around Hbar equals 0. So we make a sort of ansatz for what the solutions are going to look like. So here's a proposal for how to make a solution of the equation. And this solution is going to be a formal series. So I'll write formal. Formal series expansion in Hbar. What it looks like is pretty simple. It's just the exponential of an integral. Of some one form. So the idea is that we're going to reduce this kind of complicated second order differential equation. We're going to essentially reduce it to something first order. We're going to say, okay, I'm actually going to get the solutions just by ordinary integration, which is much simpler, right, than solving a differential equation. Now, what does this formula exactly mean? Well, first of all, I'm writing a bunch of solutions labeled by points y, and y is a point of the spectral curve. So we had this picture, right? We've got our surface downstairs, and then we've got our spectral curve. And I'm trying to produce solutions here, or in some little neighborhood here. And the way we're going to produce the solutions is by doing integrals, but not integrals on the curve. They're going to be integrals on the spectral curve. We're going to integrate a one form on the spectral curve. And so we'll get, so here's y, here's z. And so if this procedure is successful, the idea is we'll get n solutions corresponding to the n possible sheets of the spectral curve over our point. Now, okay, so does this method have a chance of working? Well, so let's, well, we got to say a little more about what this formal series is supposed to be. So this lambda twiddle formal of Hbar, so that's going to be a one form, holomorphic one form, sorry, holomorphic one form on sigma, sigma phi, written as a power series in Hbar. So lambda twiddle formal will be sum from 0 to infinity, Hbar to the n lambda n. So each lambda n now is a one form on sigma phi. And lambda 0, there was one kind of tautological one form that we had in the story, which we used last time, which is just the Liouville one form, right? Because this thing sits inside of the cotangent bundle, it has a canonical one form. And so the picture is that we're going to make a solution where it's a leading order. What we do is we just integrate that Liouville one form. But then that will not give us an exact solution. And we have to kind of iteratively upgrade it to a series in powers of Hbar. So, and now the idea is that the equation, so the equation star is going to determine the lambda n recursively. But crucially, just it's recursive, but it's completely algebraic. Even though you're solving a differential equation, this will be a completely algebraic thing. So let me show you an example. So for example, let's do the simple case n equals 2. And that this might also help explain why this ansatz is the one we take. So then the equation that we're trying to write, let's just write the equation now in our local coordinates. The equation that we're trying to solve looks like this. And then the ansatz, what's the ansatz? So at leading order, if I just write the leading order term, it looks like psi z in Hbar goes like, So how could I try to write down a solution of this equation? The most naive thing I could possibly do is to write something like this. I would write integral up to z from some z naught of the square root of minus p2 of z dz. I guess I should write z prime here. Why is this a good ansatz? Well, if you just naively take the derivative of this thing twice, right? Each time you take the derivative, it pulls down h bar inverse times the square root of minus p. So when you do it twice, you get h bar to the minus 2 times minus p2. And that's perfect. That exactly cancels the other term in the equation, right? So this looks like a solution of the equation. If you're like, in your first year differential equations class, you might think that this is exactly the solution. Of course, it's not an exact solution, but the reason why it's not an exact solution is because when you differentiate the second time, you have to differentiate the term that you pulled down the first time. That error term is subleading in h bar. It has only one power of h bar instead of 2. So what that suggests is that this will be a good ansatz to leading order in h bar. But it also shows you why you have to work on the spectral curve, because the integral, the thing you need to integrate here in order to make this machine go, you have to take the square root of minus p2. The square root of minus p2 is not defined downstairs, but it is defined on the spectral curve. So that's why we're writing an integral. We're thinking of the solution as being an integral on the spectral curve, not downstairs. Now, yeah.
Is it true that the underlying the integrated one form coincides with the Louis one?
No, the exact lambda twiddle, absolutely not. The leading term in it. So it's a series expansion in powers of h bar, and the leading term is the Liouville. Oh, here, yes. In this case, this square root of minus p2 is the Liouville in this example.
Yes, that's what I'm asking.
Yes, exactly, it is.
And does sigma tilde appear here at all?
Sigma tilde does not appear yet. Sigma tilde will appear. Oh yeah, sorry. This tilde has nothing to do with the tilde on sigma tilde. Yeah, thanks.
Yeah, no, of course this tilde doesn't, but yeah, but will sigma tilde appear?
Sigma tilde will appear when we go beyond formal series.
Okay, cool, thanks.
So far we only use sigma. Okay, so the exact ansatz now looks like, psi of z in h bar is exponential of h bar inverse integral from z to z naught of some, let me write it, s of z prime dz prime. That's lambda twiddle, but I'm writing it in local coordinate. If you plug that into the equation, you find that it has to obey the equation s squared plus p2 plus h bar times the derivative of s is 0. That's called the Riccati equation. And that equation is what you can use to determine the whole series expansion. So in this particular case, and what it leads to is this lambda twiddle formal becomes, it's given by the following formula. So the leading term is square root of minus p2. Then there's a term at order h bar, which is p2 prime divided by 4p2. Then I'll just write one more term. I just want to give you some feeling of how this thing looks. So square root of minus p times 5p2 prime squared minus 4p2 double prime divided by 32 p2 cubed plus etc. all times dz. So it's a formal series. I wrote the first 3 terms of the series. And you see that each term in the series is just given algebraically in terms of P2 and its derivatives. And particularly, you never do an integral here. All the integration has been postponed to this ansatz that involves one integral of the one form. Okay, so that's the WKB ansatz for attempting to solve these equations. And it at first looks a little bit too good to be true because, if there are literally solutions like this, then you can reduce the whole monodromy problem. Any question you want to ask about the differential equation, you can reduce to just doing abelian integrals. Just literally integrating one form, maybe complicated one form, but still. Okay. But now comes to this sort of crucial thing, and this is where the spectral network and so on get into the business. So the key thing is that this lambda twiddle formal has 0 radius of convergence. In the Hbar plane. It's a series in Hbar, just to be sure. For every value of z, we have one of these series. For every point of the curve, we have this series, and it has 0 radius of convergence, as long as there exists at least one branch point. So in all but the most trivial examples, this lambda twiddle formal has 0 radius of convergence.
And this is true for any z?
For any what?
P2 depends on z.
P2 depends on z. That's right. That's right. And I'm saying this guy, no matter what value of z you're at, this thing will have 0 radius of convergence. And the reason, I mean, I can kind of say what the reason is. The reason is that, you know, imagine that there were actually solutions like this. Imagine that this formula literally gave you a solution. Well, as we said, the solution depends on the data of a point on the spectral curve, not on the base. And in particular, if you analytically continue these solutions around a branch point, they'll have monodromy. They mix with each other because you move from one sheet of the spectral curve to the other. On the other hand, the actual equation has no singularity there, so there can't be monodromy there. So just for that reason, you see that something has to be wrong. And what's wrong is that this series has 0 radius of convergence. Okay, but now comes the good part. The good part is that despite the fact that it has 0 radius of convergence, you can do something with it. So you know, there's like standard things that you do with a series that you think should be an asymptotic series. Namely, you can try this method of Borel summation. Now, I don't want to try to say what Borel summation is. I just want to treat it as kind of a black box operation where you put in a series and you may or may not get out a function. And in this case, well, let's see. So in general, I have to say it as a conjecture, but it's a theorem for n equals. It's a theorem when I put enough conditions. So it's a theorem for n equals 2. Phi2 with at least one double pole, at least one pole of order greater than or equal to 2, and theta a generic phase, so not a BPS phase. So I'm going to say the general conjecture, but I'm just saying it's not completely nuts. It is a theorem in one case, an important case. And I should say whose theorem this is, but this is not my theorem. This was a folk theorem in the WKB literature for a long time. So there was a manuscript of Quique-Schäfke. There was an account of it by Takei. I learned the proof carefully from Dylan Allegretti. And then the most complete account, I think, is now available on the archive due to Nikita Nikolaev. Okay, so this is a theorem in this particular case. The theorem is that the formal series, lambda twiddle formal, is actually Borel summable. So to an actual one form, which I'll just call lambda twiddle, but not always. So it's Borel summable except for y lying in the spectral network. And let me write it a little precisely. So we had the spectral network was lying on this root curve W twiddle, which had 2 projections to, so the picture was sigma twiddle mapping to sigma in 2 different ways. And so the spectral network kind of naturally has a bunch of trajectories that live here. And the statement is that you can Borel sum this series almost everywhere, but not if you happen to lie on one of the lines of the spectral network, or the P1 of the spectral network, where theta is taken to be equal to the argument of Hbar. So the way the Borel summation works is for any value of Hbar, you can try to Borel sum to get the value of the function at that point. And the statement is, whether you'll be able to do it or not depends on the spectral network, but particularly the spectral network whose phase is the argument of Hbar. Okay, so I think I was asked to list kind of things that I think are interesting questions in this area. And I think one very important question is to establish this Borel summability beyond the case of second order equations. But let me try to say what, yeah.
Whether the Borel sum is unique in this case.
It's unique. Borel summation, yeah, that's right. So Borel summation, I mean, it's an absolutely constructive procedure. It produces, if it works, it produces for you a single thing. And the characteristic property that it has is roughly that, you know, the asymptotic series, yeah, what does it mean to say it's Borel summable? So properties of this lambda twiddle. So one property of lambda twiddle of Hbar is that it'll have asymptotic series expansion as Hbar goes to 0. And that asymptotic series expansion is exactly given by this lambda twiddle formal. And the other thing that's true is that it obeys the same differential equation that lambda twiddle formal was supposed to obey. So lambda twiddle formal obeyed some equation to all orders in Hbar. Lambda twiddle actually obeys that differential equation. But that's right. Oh, maybe I know what you mean. Sometimes in Borel summation, you have this thing where you run into a singularity and then you can go around it one way or the other. And so you say the summation is not unique. That's right. Here I'm talking about the situation where that doesn't happen. Yeah. Okay, so as a practical matter, what does this mean? So if suppose Z is not in the projection of the spectral network, so now down to the base. So suppose I'm in one of the domains that's cut out by this spectral network. Yeah, and now I'm going to simplify my notation. I'm just going to write L for the local system, which was phi Hbar. I'll write W for the spectral network at the phase argument of Hbar. And I'll write just sigma for sigma phi. So if Z is not in the projection of the spectral network, then we're saying that this Borel summation works for all points lying above Z. And so now this ansatz that I wrote before, now I can write it just for an honest solution, not a formal solution. I write the same ansatz, integral from y0 to y, lambda twiddle of Hbar. Now this procedure actually gives me an honest solution. And in fact, it gives n linearly independent solutions. Well, for n bigger than 2, that's a conjecture because the whole thing's a conjecture. For n equals 2, it's true. N linearly independent solutions in any simply connected domain of C, you know, omitting the projection of the spectral network. And these solutions, they depend on the base point. So I have a base point here, why not? But they depend only by a scalar multiple on the base point. So up to scalar multiple, they're completely canonical. That's the key thing, is that we started with this equation, which is just kind of a rank n thing, you know, and somehow by looking at Hbar goes to 0, we generate actual canonical solutions. It's like we diagonalize this equation. You know, they're not arbitrary up to GLN, they're just arbitrary up to C star to the n. So let me say that a little more geometrically. So what I'm saying is that L is decomposed into the direct sum of n one-dimensional local systems in any such domain over U. But in fact, the more canonical way of saying it, because those n local systems are really labeled by the n sheets of the spectral curve. So the even better way of saying it is to say it like this, we have a rank 1 local system over the spectral curve, minus some part of the walls. Well, who is this local system? The sections are just the solutions of the equation d minus h bar inverse lambda twiddle of h bar psi equals 0. The psi's that I constructed, right, they were constructed to be solutions of this equation. I was just integrating the exponential of the integral of lambda twiddle. So another way of saying it is that they solved this GL1 equation where the connection form is just this lambda twiddle. And then what we found is that the local system that we have downstairs, not everywhere, but off of the spectral network, is the push forward. Oh, let me give this local system a name. The local system upstairs, this rank 1 local system, I'll call it A. And then what we're saying is that the local system downstairs is just the push forward of a local system upstairs. That's this kind of diagonalization. Okay, so that's a sort of partial, diagonalization of the equation, not everywhere, but only away from the walls of this spectral network. Now you can actually do a little more. So I think there's not time to describe it, but let's just say there's suppose that theta, which was the argument of h bar, is not one of these BPS phases. It's not one of these phases where two walls hit each other head to head. Not a BPS phase. Then there's a canonical way to patch A to get a local system. So a priori was only over the complements of some walls, but you can actually patch it across the walls. So to get a rank 1 local system, which is over the whole over sigma minus the ramification. So literally everywhere except the ramification locus. And it has a holonomy around the ramification locus just of -1. So just a sign you should almost ignore. So around each point of pi inverse of delta C. So let me call that, I'll give that a name. I'll call that an almost local system over sigma. So essentially what we've got now, so we started with this complicated equation that we wanted to study, and now we've related it to this thing which is supposed to be simpler, which is a rank 1 GL1 local system over the spectral cover. Just to say that a little sharper, if I've got a class in the homology of the spectral cover, again with the branch locus removed, I can define just a number I'll call x gamma, which is the holonomy around gamma of the of this GL1 local system A. Then that's a function we can say something about. So we understand completely the asymptotic expansion of this function x gamma. I'll just write it, x gamma is the exponential of z twiddle gamma over h bar, where z twiddle gamma is the Borel summation of just what you get by integrating our corrected one form term by term around the cycle gamma. Okay, so what did we do? So we started with this equation we wanted to study. We built from it this GL1 connection over the spectral cover. And now I want to say, and we constructed some numbers, some kind of derived numbers, which we have a pretty good control over. In particular, we can completely control their asymptotic series to all order in Hbar. And now what I want to say is that these numbers are actually useful in practice. So here's where the cluster part will come in. Yeah.
Does this construction survive if you have everywhere dense spectral network?
It relies on this conjecture. So the case that I said is a theorem is a case where you will not get an everywhere dense spectral network. Okay, so now you ask, should it be true if the spectral network is everywhere dense?
Yeah.
I think the answer is yes. And there is some work that, obviously there's some kind of analytic difficulties that you're going to face there, right? So I think some of the necessary work was done by Aaron Fenyas in his thesis.
Sorry, can you type it? Or?
Yes, well, how about I write it here? Aaron Fenyas.
Mm-hmm.
He didn't address directly this question of the Borel summability, though. I think that I heard recently from Nikita Nikolaev that he thinks he can do the Borel summability in this case, if I'm not confused. And so as a practical matter, I think the answer should be yes. But it's not a theorem today.
Okay. Thanks.
Okay, so let's talk about what are these X gammas. So I made a big deal about these X gammas. I want to say those are some information that you might actually want. So let me go back to my example again of, so let's return to the example. Of, z cubed minus 1 dz squared in the plane. And now let me paste you another picture. So okay, so there's our picture in the plane with the 5 asymptotic domains and the spectral network drawn. So this is the picture which would be relevant for, it's the spectral network at theta equals 0. So in other words, it's Hbar real and positive. And so on it, so now I've labeled all the sheets and everything, and I've marked 2 cycles on the spectral curve, which are labeled gamma 1 and gamma 2 in this picture. And now the statement is that these abelian holonomies, so x gamma 1, it was the holonomy of this GL1 connection. The statement is that x gamma 1 in this case turns out to be equal to the cross ratio that we mentioned as something you might want to compute. So it's the cross ratio of line 1, line 2, line 3, and line 5. And similarly, x gamma 2 is the cross ratio of line, let's see, the rule for this is that I look at the quadrilateral, yeah, maybe I'll draw, well, okay, let me first write the answer and then say how you get it. So it's going to be L5, L1, L3, L4. So the data that you want, the sort of invariant data of the non-abelian connection is captured by this simpler abelianized object. Now for people who are kind of like cluster aficionados, you'll recognize this picture because according to, so I think this construction has been said in different forms by different people. I learned it from the work of Falk and Goncharov. So the cluster story in Falk and Goncharov So they say, given a triangulation of the pentagon, there's a corresponding coordinate system, what they call the cluster coordinate system, on this configuration space, con5 of CP1, which is our moduli space of flat connections in this case. And then these particular cross ratios, there are lots of cross ratios you could take, but they say that these specific cross ratios, the two that we wrote here, the cross ratios x gamma 1 and x gamma 2, they are the cluster coordinates. Yeah.
Other gain 5 points on CP1 or RP1.
Was the question whether it's CP1 or RP1?
Yeah. In the Fock-Goncharov case.
In the Fock-Goncharov, they consider both. So they do make a big deal out of the fact that their thing exists over R. So they definitely consider the case of RP1, and in fact, they even have some positivity. So it's like some positive part of the of con5 of RP1. But for this story that I'm saying about the opers, it doesn't naturally land in that part. It lands in the complex part, and certainly Fock-Goncharov also talked about the complex version. So this x gamma 1, x gamma 2 are cluster coordinates associated to a particular triangulation, and that triangulation is this one. So to this triangulation. So you see how I drew the triangulation here. I drew basically every line I could connecting the asymptotic vertices that doesn't cross one of the lines of the spectral network. And so that rule determines for you a triangulation. In this case, it's this particular triangulation. And it corresponds to the triangulation that Fock and Goncharov would have you consider. So in short, what I'm saying is, what's the message here? The message is the Fock-Goncharov cluster coordinates arise naturally as the holonomies of a natural GL1 connection. I should say rank 1 local system. Rank 1 local system up to this little twisting by -1, which for most purposes we can forget about. Rank 1 local system over spectral curve covering the original curve. And they in some sense arise automatically. So where does this local system come from? It arises automatically if you try to do this WKB analysis of the differential equation. So for the what's called the exact WKB analysis of these Schrodinger type equations. And the same thing happens in more generality than this specific example. So similarly, yeah, maybe I'll just say like 2 other examples and then I'll stop. Similarly, if we have, still with n equals 2, I take phi 2 to have at least one pole of order greater than or equal to 2. phi2 has only simple zeros. I have to put a lot of conditions. And theta is not one of these special BPS phases. So then the spectral network determines an ideal triangulation of the curve C. I think I drew the picture before. I'll draw it again. So maybe here are the poles, and here are the zeros, and there's the spectral network or Stokes graph. Then it determines a triangulation like this. And then for each edge of the triangulation, there's a corresponding cycle on the spectral curve, which looks like this, which I'll call gamma E. And then so then the statement is, so we have a local system. We have a local system built from this quadratic differential. And we can ask the same question we asked before, which is, what is that local system? Well, Fock and Goncharoff have a language for answering that. They give you the coordinates of that local system in their coordinate system. There's one coordinate for each edge. So this is the Fock-Goncharoff coordinate associated to the edge E. They would determine the local system by giving you the coordinates associated to each edge. And what I'm saying is that those coordinates are exactly equal to these abelian holonomies along the cycles, the corresponding cycles that I drew here, X gamma E. So in that sense, this business of abelianization, which you could think of as coming from trying to do the WKB analysis of OPERs, it produces the same coordinates as the Fock-Goncharoff. Of course, it produces more because it produces their asymptotic expansion. It gives you a kind of formula for actually computing them. But if you just think of them as coordinates on the moduli of flat connections, this is leading to some special coordinate system. It turns out that coordinate system is one that people already thought about. It's the Fock-Goncharoff coordinate system. And then maybe I'll just say that a similar thing happens for n bigger than 2 in examples. The X gamma recover cluster coordinates on moduli spaces of local systems. So for example, like a few examples that have been done. So for example, the cluster coordinates on GR36, you can get them all this way, or on moduli of SLN connections on a punctured surface with a specific kind of decorations that Fock and Goncharoff considered. So complete flags around every puncture. Those you can also get from this kind of spectral network business. And so the point is that those coordinates, they arise kind of automatically. If you just do the WKB analysis and you carefully follow your nose, you're led automatically to these cluster coordinates. Okay, I think maybe that's a good place to stop. And then next time I'll try to talk about the DT invariance and the hyperkähler geometry.
Okay, let's thank Andy for second talk. Questions?
I have a question. Aren't these Fock-Goncharoff coordinates the coordinates on the moduli space of framed local systems instead of decorated local systems?
Oh, I think Fock and Goncharoff use the words. Yeah, sorry, right. That's a term of art for Fock and Goncharoff, and I think indeed, I think what I said is the opposite of what they say. So, right, framed means it has these flags around the punctures, right?
Right.
Yeah. Sorry. So absolutely. So, yeah, I should use their words. So, you're right. It's framed in the language of Fock Goncharoff. Absolutely.
Thank you.
Was Hbar missing in Fogon-Chorov's construction, or it was entering implicitly in
Hbar somehow wasn't there in Fogon-Chorov. So Fogon-Chorov, you would say they're kind of studying the whole moduli space of local systems. They're studying them kind of, they're just doing something on the whole moduli space of local systems. And this business about Hbar is studying some specific curves inside the moduli space of local systems, which arise naturally, from this point of view of, actually just writing down a differential equation on a Riemann surface and trying to solve it. So from that point of view, we're analyzing a local system by fitting it into this curve, and then determining, roughly speaking, the asymptotics of this curve. Fogon-Chorov didn't think about those particular curves inside the moduli space of local systems, but they turned out to be good curves to think about. And if you do think about those curves, you're sort of automatically led to use their coordinates, even though they arrived at their coordinates in a somewhat different way.
So their coordinates are valid for any value of Hbar, but you just shown us how to derive them in Hbar to zero limits. Yes.
Well, it's more than that's right. So what I showed is how to deduce the asymptotic expansion of the coordinate as a function of Hbar. That's right. That's right. The coordinate is an actual function. It's not just a formal series. It's an actual function. And what I showed you so far is how to calculate the asymptotic expansion of that function.
Hi, Andy. I would like to ask, so in this story, you have this theta that's controlling kind of like a mutation, right? So as theta passes through the BPS phases, you do a mutation. But
yes.
I mean, theta is like, it's like, it only goes through a circle. So you only get like, I don't know, that number of seeds. So
right.
What happens to other seeds inside the cluster theory?
So you're asking, how do you see the whole cluster structure? Right. For example, in this case of a triangulated surface, how do you see all the triangulations of the surface?
Yes.
So indeed, if you just sit at a fixed quadratic differential and vary the theta, you go through some specific sequence of mutations. I think it's called a green sequence or something, but it's not all the mutations. You don't get all the seeds. Now, then you could say, suppose I also allow myself to vary the quadratic differential. In that case, I actually don't know the answer to this. Maybe someone here knows. I guess I would guess that then you can get all the triangulations, but actually, I'm not sure if I ever carefully proved that. I think that must be well known in some other language, if it's true. Benedict, do you know?
I mean, in the SL2 case, this is a result of Bridgeland-Smith, but it's not quite that result. You also need to vary the complex structure on the Riemann surface. And this is related to the discrepancy between the physical notion of stability condition and the mathematical notion, where the mathematical notion gives you twice the dimension.
Okay, good. So there's the authoritative answer.
But anyway, you will get only seeds which are associated to triangulations, right? So
well, so far I was just talking about quadratic differential. So now for higher rank, you can ask, how many seeds can we get by exploring this parameter space? So then I think it's a super interesting question. I would like to say that you get all the seeds, but I absolutely don't know. In the case of one little exploration I did is for GR36, I was kind of curious whether you can get the seed that has the non-Plucker coordinate in it. In other words, to go beyond the things that are given by bipartite graphs, and that you can do. So that one you absolutely do get. And I would conjecture, although I haven't done it carefully, that you get all 50 clusters in the case of GR36. But then going beyond that, no, I absolutely don't know whether you get the whole cluster, whether you get all the seeds or just some subset of them.
Thanks.
And so when you say that you can get a non-Plucker coordinate, is it that, so you know how if you start with this with the seed that corresponds to a triangulation, you can do these mutations at 4 valent vertices so that your graph is still planar on the surface. Can you get,
Yes.
so are you claiming that you can get some non-planar quivers, non-planar on the surface quivers?
Well, I never thought about it in terms of whether the quiver is planar or not. I mean, I just never thought in that language. But definitely, you can get mutations. You know, in this business, you get the mutations one at a time. You don't get them necessarily in this group of four.
But you can, for example, mutate at a 6-valent vertex.
You can mutate at. Yeah, I think that's right. The way you get the non-plucker is to mutate at a 6-valent vertex, right?
Yes.
I think that's right. I think in fact that's what I originally did to get it. Is to, but yeah, but I can just show you. Maybe I'll show it next time. I can just show you the quadratic and cubic differential, which have the property that they give you this non-plucker coordinate. So I don't think of it as getting by mutations. You just sit at that point and ask, what cluster do you get?
Thanks.
Okay.
Since this quiver was mentioned, so I'm just curious for things that are not triangulation, like higher rank, like how do you see the quiver from this diagram?
No, this is the thing that I don't really. Okay, so it would be beautiful to have an algorithm in the higher rank case where you start with the spectral network and you just produce the quiver. In examples, I've done it. But I don't have a general algorithm which does it. I think that's one of the super interesting problems. So there's some very weird kind of linear algebra that shows up. Yeah, maybe I'll say a little bit about that next time. I mean, you do get cluster coordinates often, but not always. Like even for the rank 2, even for the SL2, if you choose your quadratic differential to be very special, you can get these other coordinate systems, which are Fenchel-Nielsen coordinates. But then the higher rank analog of that is much wilder. You get totally crazy coordinate systems, which require you to solve what, at least to me, seem to be difficult linear algebra problems. I mean, every time you do one that doesn't have any, that's non-BPS, every time I do one so far, I always get something which you can ultimately see to be a cluster. But I don't have any general theory about that. I mean, it's just it's an experimental fact. I
mean, if you have a way to identify which functions are cluster variables, and if you can show them they're like cycles, and then you can take like some intersection form to get the quiver, maybe.
Oh yeah, well that's what you do. No, for sure, that's right. Sorry, I should have said that. I mean, once you've somehow identified which cycles are the ones that are going to be the nodes of the quiver, then for sure the arrows of the quiver just come from taking the intersection pairing on the cover. But yeah, the hard part is to figure out who's going to be the nodes of the quiver.
Okay.
I mean, for SL2, you understand it's easy, but for higher rank, at least I don't know how it's done in full generality. There are some papers by Pietro Longhi and company where they had a method of doing it in some examples, which was actually a systematic method. So it's not that no one has any idea, but
there's a big difficulty with that, in that it requires a spectral network that in the SL2 case corresponds to a Jenkins-Strebel differential, where if you think about it as a decomposition of the surface into cylinders and disks, it has no cylinders, only disks. And it's it's completely not known if these actually exist beyond the SL2 case. There's some forthcoming partial results that say you can get a spectral network with closed trajectories, but there's not the analog of this no cylinders condition.
I see. So you're saying that their thing is not very useful in practice at the moment.
Well, it depends what you mean by a network. If by a network you mean something coming from a point in the Hitchin base, then I would say beyond SL2, we don't really know how to do it. And I also know for SL2, I don't think anyone's actually written down a proof that it's the same as the Bridgeland-Smith quiver. I'm almost certain that it is, but someone should write down a proof. And But if, on the other hand, for n greater than 2, you take the viewpoint that a spectral network should just be something we can draw, and let's not worry about if it comes from a point in the Hitchin base, then there's basically the analog of the minimal networks that give you the Fock-Goncharov coordinates, but an analog in some sense. And you can draw these, and you can draw a quiver, but you don't know if it comes from a point in the Hitchin base.
But also, are you saying you could do that for every cluster, or just the ones that correspond to triangulations?
Well, yeah, just the one. I mean, these are very special networks.
Right, they're very special networks, but also very special clusters.
Yes. Yes, but I mean, it depends. Do you want the cluster, or do you just want the mutation class of the quiver?
Oh, I see. Right, that you can get. Yes, absolutely.
And you've mentioned non-BPS quivers or non-BPS mutations. What are those?
No, non-BPS phases. I just meant, the kind of generic phase. The generic phase is one where you don't have any two walls that hit each other head to head. So I call those non-BPS phases to distinguish them from the ones where like a saddle connection
that hit each other, you call non-BPS.
Right, it's BPS. It's BPS if they hit each other. It's non-BPS if they don't.
And did you say you can get you kind of know higher rank analog of Fanshawe Nielsen coordinates?
There are several. So there's a paper by Lotte Hollins and Omar Kidwai that developed what I think probably really deserves to be called like the higher rank, the most obvious analog of Fanshawe Nielsen. Then for CP1 with 3 punctures, there was a slightly wilder one, which is in a paper of mine with Lotte Hollins.
And by high rank, you mean they're honestly coordinates on SLN local systems. They're
right. Like let me talk about let me talk about the example that I know best, which is this thing of CP1 with 3 punctures. Mm-hmm. So CP1 with 3 punctures and SL3 local systems. Mm-hmm. So then, in SL2, if you freeze the holonomy around the, like if you require, say, unipotent holonomy around the punctures, then there's nothing left. There's no internal modulus. But for SL3, there are 2 moduli, and you can ask, what are they going to be? And so there, if I choose my phase and cubic differential appropriately, I can get a picture which looks extremely simple. So the spectral network looks like this. This is on CP1. This should be like the equator of CP1. I didn't draw it so well. Just like that, it just splits the thing into 2 domains. And then there's a coordinate system. There's a coordinate system associated to this, which has all the good WKB properties. I mean, it does seem to be the canonical one that comes from WKB analysis, at this particular phase. But it's super weird if you just think of it in terms of like, as like a cluster type coordinate. I mean, the weirdest thing about it is that, usually in defining these Fock-Goncharov kind of coordinates, you have to make some choice of kind of decoration data around the punctures, right? Mm-hmm. You make some choice of like a flag around each puncture. Mm-hmm. Here, you also have to make a choice, but the choice is described in some complicated way that doesn't just involve the monodromy around each puncture separately. It's some coherent thing involving the monodromy, all 3 monodromies at once. And there's, if I remember, there's a 12-fold cover of the moduli space that you encounter, which is somehow not. Yeah, I don't know what to make of this moduli space. It's what automatically comes from this WKB thing, but
I mean, why should it be surprising that we get constraints? I mean, if we think about it in the if we think about it not from putting together a series of local systems via gluons, but as taking the asymptotics, it seems natural that we might get constraints on what is the asymptotic monodromy around these turning points.
Yeah, I'm not saying it's a constraint exactly. Yeah, so these points, these are branch points, but they're also the singularities. Well, maybe I should say, just because I think it's such a fun thing, and since the question is tangentially related to it, maybe I'll say what the linear algebra problem you have to solve is. I'd actually love to know if someone has seen this before.
And so, actually, before you do that, so what exactly are we trying to do now? Just construct one more coordinate that Poisson commutes with.
We're trying to shrink two coordinates.
And
it's a two-dimensional moduli space.
They have to make they have to give a canonical pair, right?
Right. But we're trying to construct, if you like, the coordinates that naturally come from this WKB thing. But suppose I want to describe them in the kind of Fock-Gontravi way, not as coming from WKB, but just in terms of pure linear algebra that I do with the local system.
Sure.
So in the usual cases, the answer is something like, okay, you choose a basis in which the monodromies are diagonal, and you use those basis vectors to do something. Here, what you have to do is you have to find a single basis in which the matrix A has the form, all the entries can be non-zero except this one has to be 0. B, they're all non-zero except for this one. C, they can all be non-zero except for this one. And then similar constraints for the inverses in the opposite place. So it's a problem involving 3 matrices. You're looking for a special basis which puts them in this kind of special shape. And the statement is that that problem has a well, if A, B, and C have semi-simple monodromy, this problem has 12 solutions. And if they're unipotent, then it has kind of 4 plus infinity solutions. Anyway, it's a kind of funny linear algebra thing. And these kind of problems seem to show up generically when you go to the higher rank spectral networks and you look for the analog of Fenchel-Nielsen coordinates.
Let me maybe just ask one more question to that end. To define these coordinates, do you need to kind of single out one of the punctures?
No, it's no, it's completely isotropic.
I see. Thank you.
Why you have this condition that some element vanishes?
It's like another way of phrasing a kind of coplanarity condition. So like the idea is that you have, so we said there's going to be some basis of solutions, psi1, psi2, psi3 that come from the WKB.
Right.
And then there's going to be another basis of solutions out here,
Right.
psi1 prime, psi2 prime, psi3 prime. And they're not totally unrelated because these lines are Stokes curves carrying particular label, like maybe 2, 3, and 3, 2. It's a degenerate thing, so they're hitting each other head to head. And what that requires is that when I cross this line, psi1 is equal to psi1 prime. That one doesn't get changed. Psi2 and psi3 do get changed, but they stay in the same plane. So the plane spanned by psi2 and psi3 is the same as the plane spanned by psi2 prime and psi3 prime.
I see.
So WKB is guaranteed to produce things with that property. But then you can just go away and ask, well, what are all the solutions with that property? If I only know that and nothing else, can I identify which ones they are? And the answer is, as it turns out, you can, up to a discrete ambiguity.
Mm-hmm. I see. Mm-hmm. Yeah. Thanks. Okay. If we don't have, do we have more questions?
Sorry, I have a quick technical question. So the Fock-Gonchar coordinates that you mentioned are about this PGLN local systems. Here it seems it's about SLN local systems. So is there like
yes. So I think these coordinates have like very slightly more information than the Fock-Gonchar. Because as you say, it's really for SL, not PGL. And how do we see that? So I think the point is that those cycles. So I express the coordinate for the cycles gamma e for every edge. And those I think are a rational basis, but not an integer basis of the homology of the cover. And so there's very slightly more information. If I remember right, the last time I thought about this, there's very slightly more information in the homology of the cover. And so that accounts for this difference, if I'm not confused.
Thank you.
Okay, let's thank Andy one more time. And thanks. See you next week.
See you next week.